Okay, so this is for the what is it? It is called the induced EMF, ACCR.01. So it's on induced EMF. Talking about the magnitude and direction of an EMF, or in this case, we are finding it talks about finding the it says the rectangular loop of a wire is 800 millimeters long, and the width is 500 millimeters wide, and you bend the L side into semicircles. So, excuse my drawing. I tried to draw it right, but it does look kind of wonky here. But so we have this side looks better. We have a semicircular loop, which or not loop, sorry, piece right here. So we've taken a rectangular loop, right? Or why do I keep saying loop? Well, I guess it would be a loop. We've taken this and we've bent it so that it looks like this guy up here. Now we've bent it so it looks like a rainbow, and it says that we keep the W side straight, while we just bend. So we're just bending the middle here, just bending L and keeping W the same. And so then we move this curved loop at 800 meters per second. So we're going, towards our magnetic fields at 0.8 meters per second into our uniform magnetic field, which is 0.6. And it wants to know the value of the EMF induced. I like how I put a E there. Induced in the loop, as well as if the induced EMF of the loop is rotated 90 degrees, so the side leading into it is one of the curved sides, one of these curved sides. So it's a two-part problem here, and what we're going to do is one way we could look at this would be to look at the magnetic flux, as we've been learning about in class. With AC, we have this magnetic flux, and so we have B, and then it's times our W here, times X, the distance into the magnetic fields. So I'm just I think in class we've been using R. I can't remember. I don't really think it matters, but so we're going some distance. We can even say D. We're going some distance into, maybe we have been saying X. It's late, sorry. So we have this surface here, and the vertical sides are parallel to the magnetic flux, so that the flux, these sides, so it's going to be, the flux is going to be 0 here, in these areas where it is, where it is parallel. But then in the horizontal areas, here, hopefully I'm showing you, we're gonna have, it's perpendicular. So that we can go off of what we've learned in class, which has been that the magnetic flux is equal to BW. So in class we talk about so D area, right? No, sorry. So the width we talk about having to do with D theta, whereas we have area dealing with dA. So this is more like talking about the arc of the center of the arc here, where so another way we can look at this is dA equals WR d theta. R being so this is the magnitude of the area, and then R would be the radius of the circular arc of arc. And then hopefully, you know what, we might change this to X just because we're dealing with D theta, and so, or yeah, X. Let's just say X. And so as we're moving our loop, just like in our lab, as we were moving material through a magnetic field, and we were looking at the graphs and seeing that they did that sine wave graph, so that fluctuation as you moved the magnet through. So in this case, it's not a magnet, it's a circular loop, but it's just a similar scenario. And so we have this loop, and it's going in the X direction. We're going to say this is positive X direction, and into the magnetic field. And we've now derived the area element of the loop, and we can begin to plug that in to our X. So we're going to have our cosine. It's going to be cosine 90 degrees minus some theta, d theta, sorry. And so in this case, we were talking about it's perpendicular, right? And so due to it being perpendicular, that's sine 90 degrees. I'm doing little doodles here. So BWR sine 90, right? D theta. Which is also, so if we integrate that is negative B WR cosine theta. And that's, we're looking at theta going from, theta to some theta subscript type deal. So we're looking at I'm making this complicated. I'm doing my best here. So we can then plug in okay. So we have our b here, which this ends up being x, right? So I'm kind of just okay. Okay, so we're looking for our induced EMF though. So I just kind of went on a tangent there. And so we have d, negative d, and then dt. And so that's gonna get us negative d over dt, like we were learning in class. And then, oh, my cat is coming to be in the video, sorry. And we're gonna times that by d or b wx. This right here, we're bringing it down here. And so then, because that is our magnetic flux, and then we are going to negative dt, d over dt, we're gonna just, so that's bwx dx dt. And then that is equal, dx dt, that's nice, is equal to bw v, oops, and so then we can plug in negative 0.600 t times 0.500 meters, because it's 500 to the negative 10 to the negative 3. And then our v was 0.8, and I said positive x direction. That's important. So it's a positive number here. And so I don't know why I just did a division sign. So we have 0.6, oops. We have negative 0.6 times 0.5 times 0.8. Ooh, we get induced is equal to 0.240 volts. Okay. All right, let's make sure we answered these questions. So it wanted to know so we found sine 90, right? Induced EMF if the loop is rotated 90 degrees. We proved that to be the magnetic fields is equal to BWX because yeah, actually negative, sorry. So in the beginning I had said it was positive, but we had actually, after integrating, I found that it actually was it's negative, and so it's a negative BWR cosine theta, which we then simplified to be negative BWX. And so then we could plug that into our equation here, and get BWX dx over dt, carrying the negative, of course. That's very important. Then we plugged in the numbers, and we got that our the value of that was 0.240 volts. Okay. Okay, so the after you find the E induced, which equals negative 0.240 volts, that means that the induced EMF, it is negative, and I described this as being positive x direction. So if this is negative volts, then that means that the induced EMF is going in the opposite direction of the magnetic field. And so yeah, so that means the direction is negative x direction that it's going. So then to make sure that we've covered all our bases, the second part of the question is asking what the induced EMF is if the loop is rotated 90 degrees. So the side leading into the magnetic field is the one of the curved sides, meaning I'm not at all an artist here. But we have our magnetic field, which I always only draw 1/2 of the arrow. And so what we're going to do here is looking at B, we now have 2L over pi is equal to x, or is equal times x. And so we're gonna go off of here, and we're going to do negative d b dt, which is equal to negative b 2L divided by pi v, and then that's negative 0.600t times 2 0.8 meters pi, because it's half a loop, if I didn't mention that. Half a loop is pi. And then 0.800 meters per second. And then we have negative, 2 times, divided by pi times 0.6 times 0.8. I get the induced to be negative 0.244 volts. So the induced EMF is 0.244 volts in the scenario where we're going in right here with L and L. So 2L, half the semicircle is pi. Okay.